only for just Sarah would be like, what is that? That's wrong.
What? So did I.
We're kind of gossiping about the other students at the moment. But
Dude,
in front of
don't you know, you're not supposed to gossip when the student is around. Oh, you have so much to learn. Anyways, what were you saying about her? I hope only good things.
No,
Wait, who was the last person you were talking about?
I was about to speak about Marana and then said what?
Okay.
Miranda, don't get me started on Miranda. She's a piece of work. You know it? Okay. So, the last vectors thing now. Okay, let me zoom in a bit.
Can I make sure one thing before you start? This is the last vector, right? So tomorrow when we come to class or on Monday, Wednesday, listen one, right?
Yes, we will start new chapter on Monday's class. Okay, so, you all see? Yeah, good. So the last thing in vectors is not, hey listen, come on. The last thing in vectors here is not very common in the exam. It's only come up maybe once, maybe twice. Well, it's come up once, maybe twice. So it's all just short little vector proofs. And I've just given some examples here. They're not too difficult. I'll start off with the first one there. So let me write it down. So the first one is, you need to prove that x dot x is the same as the magnitude of x squared. So what you could do is the left hand side and the right hand side separately and see if they're the same. So on the left, that would be x1, x2, x3 dot x1, x2, x3 equals squared square root. Actually, before I'm doing too much on one line, let me just go back a bit. Come on, undo. x1, x2, x3 magnitude squared. So on the left you'll get x1 squared plus x2 squared plus x3 squared. And then on the right you get square root squared x1 squared plus x2 squared plus x3 squared. So here you get x1 squared plus x2 squared plus x3 squared equals x1 squared plus x2 squared plus x3 squared. So you can see that the result here, it tells us that what we started with is true. In fact, x dot x does equal magnitude of x squared. Okay, next one here. So, prove that A dot B equals B dot A. So we can do that in a similar way. A dot B equals A1, A2, A3 dot B1, B2, B3, which would equal A1, B1 plus A2, B2 plus A3, B3. But if I wrote it backwards, B dot A, that would be B1, B2, B3 dot A1, A2, A3, which would equal B1, A1 plus B2, A2 plus B3, A3, which is the same thing actually, A1, B1 plus A2, B2 plus A3, B3. So therefore, A dot B equals B dot A. Oh yeah, it's a cut off at the bottom. You writing this down, Brandon? Yeah. Okay, so next one now. Okay, so I would like just for a minute or two for you to try to do number 3, because I've done number 1 and 2, so you might get the idea of how these go. But in number 3, I'd like you to show that A dot B plus C equals A dot B plus A dot C. So I think most of you should be able to try and do this successfully. So just for a minute or two, try it, and then I'll give you the answer. So it's A dot B plus C equals A dot B plus A dot C. So in other words, you're proving that the expanding that you've done in algebra is also true for dot products. So try to prove that one. So the one you're trying to do now is A dot B plus C is the same as A dot B plus A dot C. So try that.
There's no numbers in this question?
Just like before, A1, 2, 3, B1, 2, 3. Oh, yeah, no, it's, usually not, no.
Okay, just take that. That's it. You're literally being
Okay, does anybody think they've got it? Maybe. Let's have a look at it. So on the left here, A1, A2, A3, dot, bracket, B1, B2, B3, plus C1, C2, C3. That will equal A1, A2, A3, dot, B1 plus C1, B2 plus C2, B3 plus C3, which would equal A1, B1 plus A1, C1 plus A2, B2 plus A2, C2 plus A3, B3 plus A3, C3. Now let's start at the right hand side and see if it matches up. So on the right we have...
We should do both sides.
Yes. AB plus AC. So AB plus A dot B plus B dot C equals A1, A2, A3 dot B1, B2, B3 plus B1, B2, B3 dot C1, C2, C3, which would equal A1, B1 plus A2, B2 plus A3, B3 plus B1, C1 plus... Sorry, did I write it down wrong? Ah, rats. Wait, no. AB plus AC. Did I write it down wrong here? Ah, this should have been a... that should have been an A, which just means they should have been A's. Thank you. AC. A1, 2, 3. So here is A1C1, A1C1 plus A2C2 plus A3C3. Now did they match up? It looks good. Let's see. So we have A1, A1B1, A1, A1C1, A2B2, A2B2, A2C2, A2C2, A3B3, A3B3, A3C3, A3C3, C3PO, and R2D2. Okay. What? Oh, you know what I'm talking about at the end, yes? Okay, so that's that one there. Yep. It's very good. I don't like that movie. Okay. Number 4.
Can you see the answer, please?
Oh, you didn't write it down? All right. Hurry up, please.
And you're like, I don't like that movie, okay?
Quick.
Okay, that's fine.
Yes?
Yeah.
All right. So the next one you see is very, very similar. In fact, I think if I do number 5 first, it will help me with number 4. So number 5 says if you have C multiplying A dot C multiplying B, then that's the same as taking the C1 and the C2 out in front from the vectors and then dotting A and B. Well, that should say A and B. It doesn't really matter though. So let me show you that one. So what I want to show here is C1, A1, and to make it clear, that's the vector there, dot C2, sorry, I'll just call it A, not A1, B, and that's the vector. That's the same as C1 multiplies C2, and then A dot B. In other words, you're allowed to take constants out in front. So on the left here, we would have C1A1, C1A2, C1A3, dot C2B1, C2B2, C2B3. And on the right here, we would have C1C2, and then here A1, A2, A3, dot B1, B2, B3. Oops. Sorry, that's B1, 2, 3. So on the left, you get C1, C2, A1, B1, plus C1, C2, A2, B2, plus C1, C3, C1, C2, A3, B3. That's on the left. But then on the right, you'd get C1, C2, bracket, A1, B1, plus A2, B2, plus A3, B3. And that's on the right. And when you look at them, they're actually the same. So if you want, you can say here is C1, C2, A1, B1, plus C1, C2, A2, B2, plus C1, C2, A3, B3. And that is the same. So in other words, you can pretty much pull constants out into the front of vectors. Got that? Not yet. I'm missing Avenue, Albaharna, and somebody else. Sayun, she's right there. Okay. Next one now. So in number 4, it looks very similar to number 3. You have to prove the same thing, except there's just an or multiplying the b. So what I need you to show for this one is that a dot or b, wasn't that it? Plus c? Yeah. Plus c. I have to show that that equals or a dot b plus c. That's what I need to show. Okay. Well, let me just get rid of that piece at the end and I'll get to it. So firstly, I think this was question number 4. The one I just did there was 3 and 5. Okay. from question number 3, we've shown that this can be written as A dot or B plus A dot C. That was from question 3, which is a lot like, 1A dot or B plus A dot C. And then we showed from question 5 that the 1 and the or can be taken in front as 1 times or, so that'd be or A dot B plus A dot C. And then that's the end of that proof. So we're able now to start grouping our smaller proofs together to make it quicker to do larger proofs. But of course in the exam that would only work if you knew the other rules were true, which you usually don't. It's usually done the way I did it earlier. Got that? No?
Like the question doesn't have
What? What are you talking about?
this doesn't equal the other.
Because what it says, not AC, but it just says. Oh, it's because when you wrote down the other time.
I'm tired. And anyways, it's gone now, isn't it? The bad maths is gone now. Okay. What's wrong?
We're discussing iron something else. Discussing that.
Did you just shush her? Alright, come on. Next one now, I did number 5. Number 6, I actually did a couple of classes ago. Just so you have some vocabulary here, orthogonal also means perpendicular. It's a little bit different. I want to show that two vectors are perpendicular if and only if A dot B equals 0. So just to be careful with the English here, if and only if means you have to show this. A is perpendicular to B. We need to show that that means A dot B equals 0. And then we also have to show it in the opposite direction. Okay, so in fact, to do this properly, we need to go both directions for the proof. So first we start off with this side. A is perpendicular to B. Again, I won't bother writing my little arrows on top. A is perpendicular to B. That means the angle between A and B is 90 degrees. What's the formula for angle between two vectors? That's A dot B over magnitude A times magnitude B equals cos 90. But cos 90 is equal to 0, yeah? So we have this result. And I'm allowed to bring this up to the right. And I'm only allowed to do that because in the question I told you that these are non-zero. In other words, they do have a length. They're not the 0, 0, 0 vector. So then we have the result. A dot B equals 0. So that's proved it in one direction. Now we have to prove it in the opposite direction, which is, believe it or not, more or less the same for this type of problem. So going in the opposite direction now? Or do you need a minute to write that? Yep. Reem, stay focused now. Stay focused. Can I move on now? Yes? Okay. So now we want to start from the fact that the dot product is 0 and conclude that the angle between them must be 90. So I start from here. So since, oh, and if you want you can write at this step as well, since A is not 0 and B is not 0. Okay. Now, since A and B are not 0, we can divide both sides by the magnitude of A times the magnitude of B. So dividing both sides by that, we get this result here. Okay? Now, of course, on the right we get 0. So we have A dot B over magnitude A, magnitude B equals 0. But we know what this is on the left. What does this equal on the left? Now, what formula is this, of course? Cos theta equals 0. Now, you might think you're finished there with that, but you're not quite finished, because now we have to solve this. So we have to think back to semester 1. So solving this, first we say theta equals cos inverse 0. So we get theta equals 90 degrees. But you have to remember there's a second answer, which is 360 minus the first answer, which is 270. So we've done the I part, now we have to do the E part. So how many answers do we have in total? But how many should we have? No. So this equation here, in this equation I did not specify any range for theta. So in fact theta is all real numbers here. So we actually have infinite number of answers. But it doesn't matter. How do we make the extra answers? What do we do? Very good. We add 360. And then if we need more answers, what do we do? Add 360 again. So in other words, all our answers can be written like this. 90, 270, and then you add 360. Okay? So that would be 360 plus 90 and 360 plus 270. So what's that? 450, and then what's the next one there? 630, is it? Okay. And don't forget, you can also go in the opposite direction. You can minus 360 because we're allowed to have negative answers. So, what would that be? Minus 270. Yeah, so dot, dot, dot. Minus 270, 90, 270, etc. You get the idea. So you get lots of answers here. But we just need to show that they're perpendicular. And when you look at each answer, it is. The first answer, the angle between them is 90. So that's done, it's perpendicular. But the second one, the angle between them is 270. So hang on, let me draw it a little bit clearer. This is angle 90. And then the second one here is angle 270. But if that's 270, how much is this one here? 90. Now what about minus 270? Well, minus 270, if you wanted to, you could say that's the other way around. So you go backwards this way, 270. Doesn't really matter because what you're left with here is still 90. So all of these angles will create two vectors that are perpendicular. So all real answers result in perpendicular vectors. what number was this?
6.
This was 6, yeah. Up? Here or further? Here? Yeah. Okay. You have that one? Not yet? Yeah. So we have the result now. If A and B are perpendicular, then A dot B equals 0. And if A dot B equals 0, then that means they're perpendicular. The next one's an interesting one. It's actually the only one in this list here that I gave you that is a not proof. So what I want here is to show that if A dot x equals A dot y, then it is not necessarily the case that A is equal to y. So in other words, you can't cancel the A in front. So with the not proofs, a proof that is always to do with a not, you can prove it by giving one example that proves it's wrong. And if you think about it, if I said something like as an example, let's see, what would be a good example? Oh yeah, if I said all Saudi students are shorter than 1 meter, would that be right or wrong? All Saudi students are shorter than 1 meter. That definitely be wrong. But the way you can prove that that's wrong is you just need one example. Because if you just had one example, then that proves that not all of them are less than 1 meter. So the not proofs are the easy ones to do because you just need one example to prove that it's wrong. So I need to prove that the following is wrong. That A dot x equals A dot y, then that means x is equal to y. I need to prove that that statement is wrong. So we just need to put in some numbers as an example. So let's say, example, A equals 1, 2, 3, x equals 1, 1, 1, and then this is where you have to be careful because we still need this we need this left hand side to be true, but we need to show that it does not follow that the right hand side is true. So far what's A dot x here? What would A dot x be? A dot x, what would it be? No, A dot x, what would it be?
1 plus 2.
Yeah, yes, which is 6. So we need to pick now a y so that A dot y will also be 6. So a very simple example I can think of would be 0, 0, 2, because now A dot y you can see will be 6. Yep. So it's true that A dot x is equal to A dot y. Because you can test it, you get 6 equals 6. But you can see that it's false to say that x is equal to y, because, you know, it's clearly not. X is 1, 1, 1, and that's definitely not equal to 0, 0, 2. So therefore, A dot x equals A dot y. It's not necessarily the case, it does not follow that x is equal to y. So the result here is that you cannot cancel A when you have dot products. So this is one way that makes it different to algebra you did before, that you cannot cancel both sides by A here.
What number is this?
7, yeah. Stick. Don't do that. All right, 8 now. Prove. Oh, you need to go back. Okay. 8 now. We need to prove that B times A dot C minus C times A dot B is perpendicular to A. And if it helps a little bit, right, listen, if it helps, A dot C is a number or a vector? Is it a scalar or a vector, A dot C? No, A dot C is a scalar, it's a number. A dot C is a number. So this is a number times vector B minus a number times vector C. It will be a vector.
Why is there the vector sign?
Ah, but there's a dot here. Maybe, sorry, you can't see. I'll write it down here. B, okay, so maybe to make it a bit clearer. I want you to prove that A vector is perpendicular to this vector. A dot C, I'm not going to write the vector symbol in, it takes too much time and energy. A is perpendicular to A dot C multiply B. Is that right so far? A dot C multiply B minus ABC. Okay. Minus A dot B times C. So I want you to prove that those two vectors are perpendicular. I'll give you a minute to try it. Try to prove this.
In the exam, we must add the vector sign.
Nope, you don't have to.
So if you forgot it, that's fine.
That's fine, yep. Yep. In fact, in the exam, they don't use the vector sign. To show that something's a vector, they type it in bold font. You know what I'm saying? You know bold font, don't you?
Yeah. They bite.
They type it in a bold font. What?
They type the question in bold.
Oh no, the letter. So the A, B, and C here would be in bold font.
Oh.
Yes. Prove this for me. Prove that A is perpendicular to that vector, A dot C times B minus A dot B times C. No, I'm actually going to do it now. So if you look up, to prove it's perpendicular, I will calculate the dot product and see what I get. I should get 0. So we know that the dot product obeys the expanding rule. We proved that earlier. So we can write A dot A dot C B brackets minus A dot brackets A dot B C. And also we proved earlier that when you have a constant, which is what you have here, you can take it out in front. And when you have a constant like we do here, we can take it out in front. So we get A dot C times A dot B minus A dot B times A dot C. But these are just regular multiplications now, a number multiplying a number. So you can write this as A dot C minus A dot B minus A dot C times A dot B, which would of course equal 0. So therefore perpendicular. This one here? So I'm going to write in what rules I used, okay? So the first one, what I used was question number 3. So I used my result from number 3 here. Then in the next one, what I did was use my result from number 5. Let me zoom out a bit and explain. I'm getting off my seat to explain. That means I mean business. Alright. So if you look up, first line is just me doing A dot that big vector. But if you just look past the fact that A dot C is a number, right? So just instead of thinking about it as A dot C, just think about it as C1 or S1 or lambda or whatever. So you have A dot number B minus number C. But even forget about that. You can even just think about it like this. A dot vector X minus vector Y. A dot vector minus vector. So the first thing I did was just to literally expand it. So you see the first bracket here, that's A dot X minus A dot Y. That's what's happening first. So that's what I mean when I say question number 3. I just expanded like I did in number 3. Now if you look at number 5, if you think about it, the A dot C, that's actually just like a number, like C1. So you remember I said if you have a vector multiplying a number, you can just put the number out in front. Just like in integration, if you multiply by a number, you can put the number out in front. Just like when you have brackets, when you have a number, you can put it out in front. So all I'm doing is pulling the A dot C, which is a number, out in front. Likewise, the A dot B, which is a number, gets pulled out in front. But what we're left with now is a number multiply a number. Just regular numbers. So they can be swapped around if I like. 3 times 4, 4 times 3. So on this line here, I just swapped the last two to make it really clear that these two, whatever they are, is the same as these two. And when you subtract them, you get 0. Now, I also told you, or you also showed me, from number 6, that if the dot product is 0, then they must be perpendicular. So the proof is finished. You've shown that A and that long vector ACB minus ABC, they are actually 2 perpendicular vectors. I saw, when I said that 2 came up on the exam, there might have been one similar to this. Let me check what the next one is. Yeah. That one I just did for you, I think that one, something not quite as difficult, but something like it was in the exam. Not quite as difficult though. I think this actually, when I think about this, I think this has only actually come up once, so it's not so common. I've just seen it once in 6 years. Okay, next one now. So this one now, or maybe we'll just finish with this one. Prove by using vectors that if the diagonals of a rectangle are perpendicular, then the rectangle must be a square. So what I mean by that is, you need to prove that if you have a rectangle, and if these two diagonals are in fact perpendicular, then it must be because you have a square. So how can we prove this? Well, the way we prove it is first by writing the problem as a vector. So we call this point O, this A, this B, and this one here C. Now, I know as a starting point that diagonals are perpendicular. So who can tell me as a vector equation or a vector statement, if I know these diagonals are perpendicular, then what? Their dot product is 0. The dot product of what vectors? What letters?
CA and OB.
Good. CA dot OB, or just B, whatever you want to call it. We know that that does equal 0. Now, what does CA equal? Well, that's A minus C. And what does OB equal? Well, that's just B. Now, we know that we are allowed to expand. So we get A dot B minus C dot B equal 0. Okay, so far? So we get A dot B equals C dot B. But if you were to look at this, I know I have a few different letters, but don't forget, because it's a rectangle, some vectors are the same. So if I go back to the diagram, vector, for example, B. If I just want to keep it with just two vectors, I should maybe use A and B, for example, or A and C. I should change one of these. I think I'll change my C because I only have one C. So what could C be rewritten as? C is OC, and what's the same as OC? AB. So rather than having C, instead I'll go back to making this minus equals 0. So instead of having C, what did we say? It was AB, wasn't it? AB dot B. And once again, A dot B minus, and then here would be B minus A dot B equals 0. Okay. So A dot B minus B dot B plus minus B dot B, and then here is minus minus plus A dot B equal 0. Okay. Now let's see where I'm going with this. Ah, rats. Yeah, I actually don't want A and B, I want A and C. Do I? Students. Traveling back in time. Alright. I would like to keep with A and C, so I need to change my B. So what can I say B is equal to if I just want to use my A's and my C's? I could say B is equal to B is equal to OA plus AB. Yeah? And what does OA equal? A. And what does AB equal?
C.
C. Yeah, OC, C. So I can just replace B with A plus C. That's what I'm going to do. So B gets replaced with A plus C. So B gets replaced with A plus C. And B gets replaced with A plus C. Equals 0. Okay, so that's A dot A plus A dot C minus C dot A minus C dot C equals 0. Now, you know that dot product you can swap. So that's A dot C minus A dot C. Now what happens in the middle here? They cancel. So I'm left with A dot A minus C dot C equals 0. But does anybody remember what A dot A is? I think it might have been my first question I did. What's A dot A? It's the square of the length of the magnitude. So here we'd have A squared minus C squared equals 0. So here we get A squared equals C squared. So here we have the length of A equals the length of C. Now if you go back to your diagram, that's the reason I chose A and C here. Because A is the horizontal one, wasn't it? And C was the vertical one. So what have I done? I've said that the length of A and C are the same. So the length for A and the length for C are the same. Therefore, it's a square. Because remember, I started off by saying it is a rectangle whose diagonals are perpendicular. Now we know it's a rectangle, and then if the sides have the same length, it forces it to be a square. So if it's a rectangle, and if the diagonals are perpendicular, then it absolutely must be a square. Of all the questions I did, the one I think that's most likely to come up in the exam, if it did come up, might be this one here. And I should also tell you that in the exam, you notice that for this question, I assumed some results that I proved earlier today. There's a few of them that you're allowed to assume. And I'll tell you which ones you're allowed to assume to be true without proof, unless they ask you to prove it. And the ones that you can assume will be the following. So you're... What? Hurry up. I'll give you about 15 seconds. You have 3 seconds left. Good for you. So the ones you're allowed to assume is true without proof, unless of course they ask you to prove it, are the following. X dot y equals y dot x. X dot x equals the magnitude of x squared. You can also assume that you're allowed to pull constants out in the front. And finally, you're allowed to assume that x dot y plus z equals x dot y plus x dot z. And like I said, you can use these in your proof, unless, of course, you're being asked to prove something basic like that. So, just before you go now, okay, there's one I'd like you to try at home for the next class, okay? And it's the one, I don't have a pen, but you might remember it from middle school. You have a circle, okay? And then you draw a line across the diameter, and you go up and make a triangle touching the edge of the circle. Do you know this one? So you have a circle, yes? And you draw a triangle where the base is the diameter, and it goes up and tips the top of the circle. And we know something special about this angle at the top. What is it? It must be 90. So I would like you to prove that if you have a circle and if you have the diameter and you have this triangle, that the angle you make is 90. Now how would you rephrase that as a vector statement? Well, that's the same as saying that this vector is perpendicular to the other vector. And then you see you get the proof started this way, like in my example with the rectangle. Yeah? I see lots of good head nodding. This is a satisfying way to end the vectors chapter. So we'll leave it there.